everyone. Today I'll be presenting a study on robustness and semantic understanding of visual models. So this body of work, the overarching theme is robustness, and there's two aspects to this. We have real-world deployments, so we're looking at how models respond to real-world distribution shifts, and from those findings, how we can improve those models. And then on the other side, we want to peek into the black box. So a lot of these architectures are black box architectures. So we want to probe them for their behavior, and based off of those findings, see how we can improve those models. So the motivation for this is benchmarking robustness is very important because these products need to be safe and the users need to be able to trust them. So here are some examples of those kinds of failures that we have seen in the real world. It's also very important for us to understand why these models behave the way they do, especially with the emergence of ChatGPT. Government agencies are looking into requiring developers to make sure they understand their models before deploying them. So some of the architectures we're going to talk about today, we have visual models, which just take video or images, and we have visual language models that take both video, images, and text. And so these are going to be a combination of transformers or convolutional neural networks. And with visual language models, there's a lot of variations of the architecture we can use. So for example, these are modality-specific encoders, and we can also have cross-attention that take those outputs and cross-attend them as well. So there's a lot of variations we'll be talking about. So the outline is we're going to talk about 4 bodies of work. The first is interpretable graphs for video language models. The second is robustness of video models, robustness of video language models, and then finally conceptual robustness of visual language models. So first, interpretable graphs for video language modeling. So this work is looking at instructional videos, which are long, complex actions. And these long videos have a lot of sub-actions that have lots of temporal and spatial relationships. So we're interested in seeing how can we use video language models to summarize them in a visual way. So the motivation for this is we want to generate a knowledge graph using our language and text, our language and video, and we also want to use audio as well. And the reason for this is existing bodies of work require lots of dense annotations, and this is very expensive to collect. So we want to do this in a self-supervised way using the 3 modalities to try and help with that. So now we'll talk about our approach. We start with first encoding vision and audio together. So we'll have our dual encoders here, and the output of that goes into a cross-attention mechanism, very similar to a transformer architecture. So we attend to one embedding using the other and vice versa, and combine those to create a joint embedding. Next, we want to initialize our nodes using word2vec. And so how we do that is we're extracting nouns and verbs from the automatic speech recognition, using a word2vec embedder to make those embeddings for those words. Then we're going to refine those node embeddings by attending to them via our joint embedding from the video and audio space to see which nodes might be most relevant to this video. So then we want to refine our node embeddings even further to have those temporal relationships between them and to also have those spatial relationships to them as well. So our message passing operations are going to be time-wise convolutions and node-wise convolutions. And finally, to get our overall graph embedding, we're going to use a readout operation, which aggregates all those node embeddings. So one of the important aspects of this is this graph needs to be interpretable. So what we do is at each message passing iteration, what we're doing is we're collecting the most relevant nodes based off of their attention values. So during each message passing iteration, we're collecting those max pooling locations to generate a map, like a mask that we're going to place over our initial node embed, or our initial nodes based off of these words. So that is how we're mapping back our most relevant nodes to the original words. Now a little bit about how we're going to build these graphs. First, we have our directed graph, which is going to try and preserve that temporal element. So we start by aggregating the node embeddings for each node instance in a time segment. Then our edge weights become the similarity between nodes in one time segment and the next time segment. And our node weights are going to be the sum of their node embeddings, which represents their attention values. So undirected is very similar, but this time we're aggregating over all time segments. And so similarly, the edge weights will be the similarity between the nodes, and our node weights will be the sum of those attention values. So now we'll talk about how we fine-tune this approach. So we're going to use a very simple triplet loss, where we use our graph readouts as our input into this triplet loss. And we're going to use an anchor video, which is our original uncorrupted video. We're going to use an augmented video with some corrupted noise as our positive sample. And as our negative sample, we're going to use another video that is not related to the anchor video. So the data sets we use is first is How to 100 Million, which is a YouTube data set with automatic speech recognition as our language signal and the video as our visual signal. And we're going to focus on videos that have craft or do-it-yourself activities. Next is Coin, which has more everyday activities such as refilling your car or changing a tire. And finally, UCook2 is a long cooking data set, so it has long cooking instructional videos. So I'm going to walk through an example, and this is an example of an undirected graph of do-it-yourself plush. And here the node size represents the relevance of the node, and the edge thickness represents the weights between them. Here we have the nouns are in the darker colors, and the lighter colors are the nouns, and the darker colors are the verbs. So now we're going to walk through some tag segments where we can see some of the nodes being activated. So now we're going to talk about a directed version of this graph. So this is where we're looking at those temporal relationship between the nodes. So here we have the nouns as our nodes, and the edges are actually represented by the verbs between them. And the darkness of the color represents the node's relevance to the video. So this is how to change a shower head. So just to get a little bit more about how useful these graphs are, we asked some users to annotate these. So we showed them a graph and 4 videos and asked them to match the correct video to the graph. And we did the reverse too, where we showed them a video and asked them to choose between 4 graphs to match that. And we found that users were more correct at matching the graph to the video than vice versa. We're also interested in understanding how there might be a global learning of tasks or a more local version of those videos. So here we're comparing the different tasks of a data set, and we're also looking at the node overlap between the graphs that they're building. So here we see the coin data set has very different activities, and that is represented by how unsimilar the activities are to each other. Versus cooking, there's a lot of overlapping sub-activities that happen, and so there's a lot more similarity there. So we're also interested in seeing how we could combine videos into one graph. So here we're showing video where we have 2 videos from different tasks and 2 videos from the same task. And as you can see, the 2 videos from different tasks, there is no clustering that share, there's no bridges, none of that. But when we have 2 tasks, 2 videos from the same task, we see that there's some overlying bridges and some clustering that happens together. So learning kind of a global look of those tasks. So in summary, this work, we proposed a new task, which was representing instructional videos in a semantically meaningful way without using any annotations. We proposed SPGraph to tackle this using video and audio and text modalities. But we also proposed semantic assignment to make them more interpretable. So now we're going to move into the robustness of video models. So here we're focusing on action recognition models, and this is where we're passing a video to a video encoder and predicting the activity in the video. So action recognition is important because there's lots of real world examples of how this is used, such as visual surveillance, video retrieval, and so much more. So the motivation for this is the existing body of work focuses primarily in the image space. So we need some benchmarks for the video space as well. And we also need just not only simulated perturbations of these real world distribution shifts, we also want to curate some real videos that represent them. So we want to look at how the model performance is impacted by these natural distribution shifts. So our benchmark does both. It simulates real world perturbations, so we're perturbing the video, and we also add some video specific perturbations, those that focus on temporal elements or camera elements that we've seen in video. And we're also using a curated data set of real world videos that will have uncommon distribution shifts as well. And we're going to provide a deep analysis on state-of-the-art models in action recognition with a combination of CNN architectures and transformer-based architectures. So here's a summary of the video perturbations that are used. We have 5 high-level categories with some examples over here. For example, freeze represents like a real-time buffering. We have random noise, camera like random rotation to represent a shaky camera. We have digital, which represents compression algorithms, and blur. So the data sets we use are very commonly used in action recognition. So the first is UCF 101 with 101 classes, HMDB 51 with 51, Kinetics 400 with 400, and something version 2 with 174. So we also curated data set to represent real videos instead of simulating them. So we collected around 4,700 clips using 47 action classes. And the way we did this is we queried for the action class in the uncommon distribution shift. So up here we have an example of that, where on the top row are frames from the original UCF 101 dataset for that action class. And on the bottom, we have our distribution shift. So for example, here we have a balance beam activity where we're changing the actor from a human to a cat. And another example over here is a marching band, but we're changing the lighting to be extremely dark and difficult to see. And so we also categorize these distribution shifts into higher level categories so we can better understand what areas models are struggling or doing well at. So now I'll provide some of our insights. So the first is looking at that spatial noise. So that was that Gaussian noise example you saw. And what we find is that models for all data sets are very sensitive to subtle addition of noise. So here we have on the x-axis the severity of the perturbation from 0, meaning no corruption was added, to 5, the most severe corruption. And on the y-axis, we have the accuracy for each data set. And as you can see, all models decline as the severity increases. One interesting observation is also that models were more robust to shaky camera versus static camera, which just means the static cameras are rotating and keeping it consistent throughout all the frames, versus shaky, it changes a lot. So this may indicate that the models are robust because the original data set has a lot of shaky camera, or it might have something to do with the variation getting closer to the original. And finally, as you can see from this table, transformer-based architectures here are typically more robust than the CNN-based architectures here on all of the data sets. Now, because videos are very important to have temporal information, we're going to look at the temporal aspects of these models. So as you can see here, models are quite robust on the kinetics data set. So on the x-axis, we have some temporal perturbations. And here, this line represents the original score on the clean data set, and the bar represents the score on the perturbed data set. And you can see the drops are quite small, but then when you look at that something version 2 data set, the drops are quite significant. And this is the case with all the other data sets as well. The drop is small. So just to get a better idea of why this might be happening, we realize that some of the classes actually can be reversed and mean another class. So for example, unfolding something and folding something in the reverse might be the other. So this is a problem as well. However, when we show the transformer-based architecture here and the CNN-based architecture here, we show the feature embeddings of these classes. We can see that on the clean data set, both models are quite good and have tight clusters. However, when we reverse the order of the sample frame, we see the transformer model still maintains these clusters, but the CNN-based model, it maintains some, but a lot get distributed elsewhere. So again, we're seeing that these transformer-based architectures might be more robust. To see this even further, we created a confusion matrix to show the different classes. And as you can see in the CNN-based approach, these vertical lines indicate that they're over-predicting on some of the classes when the samples get reversed or are altered in a temporal way, while the transformer model is much stronger. We're also interested in how we can make models more robust. So we look at pre-training and how that might improve robustness. So here we have models that are trained on UCF 101 or HMDB from scratch, or pre-trained on Kinetics 400 and then fine-tuned on the data set. And as you can see, especially with HMDB, that the model becomes more robust after if you pre-trained it on the Kinetics data set. We do see, however, that certain perturbation categories might not be as robust. For example, compression. You can see that some of the models actually are less robust than when trained from scratch. And we see this over here as well when we're aggregating across the models, the severity 0 to 5 again. We can see that the pre-trained model, the performance decreases at a certain point over the trained from scratch model for that compression-based algorithms. So another thing, we want to look at how model capacity improves robustness as well. Previous works have said the larger and more model capacity, the more robust, but we don't find this is consistent in this case. So for example, we have our CNN-based approaches, and here we see X3D, the smaller approach, is very competitive with the others. Just to be more clear, on the x-axis, we have accuracy. On the y-axis, we have the relative drop in performance from when tested on clean data versus our perturbed data. So the idea is to have our models in this top corner. And the size of these nodes represent the model capacity. So again, with these the transformer-based architectures, we also see that the smaller model isn't just as competitive as the transformer. And then we look at the other data sets as well. We said that even here, the CNN-based approach is competitive with the larger transformer-based architecture. So we're seeing some inconsistencies here with the model capacity and robustness. So another way we want to look at how we can improve robustness is how does training of different perturbations improve? So we have 3 categories of perturbations we're going to train these models on. The first is mixed, where we use all combinations of the perturbations. We randomly select half to train on and half to validate on. And we do the same with temporal and spatial, but just focusing on those temporal perturbations and those spatial perturbations. We had another category, which is called PixMix. It's a recently proposed data augmentation technique for images. And we're extending this to video. And what it does is it adds a fractal image overlaid. And here's a dramatized version of that for video and what that might look like. So we're going to focus on the results of just the spatial and temporal to see how those corruptions impact each other. So on the x-axis, we have all of our perturbation categories. On the y-axis, we have what perturbations the models are trained out. And here we're looking at a CNN-based approach, ResNet 50, and a transformer-based approach, MVIT. So I'm just looking on the models on the clean data. We see that both types of perturbations, when they're trained on them, actually improve the original score on the clean data. So that does help that. And then when we look at how training on one might impact the other, we see that on the CNN-based approach, training on both spatial and temporal help each other in both areas. However, when we look at the transformer-based architecture, we see some differences, and we see especially that when trained on spatial, the performance actually decreases on the temporal perturbations. So this might indicate that different architectures are helped by data augmentation training than others. So now we're going to go to analyze those curated videos. So here's an example of them again. And so we have the models on our y-axis here, and those high-level categories I mentioned for those curated distribution shifts here. And what we see just by glancing here is that the transformer architecture typically seems to be more robust compared to the CNN-based architectures. When looking on training those models on those perturbation categories, we see again that these these CNN-based architectures are improving. So these numbers are actually looking at the change in performance on the UCF1DS data set when not trained on our perturbed data set versus trained. So greater than 1 means that it improved, 1 means it's the same, and less than 1 means it actually worsened the performance. So in summary, our findings indicate that transformers are typically more robust. CNNs may benefit from our data augmentation or just different types of architectures. Pre-training does improve robustness in most of the perturbation categories. And some models are very robust to temporal aspects. However, when the data sets are more temporally complicated, like the something version 2, they're not doing very good. And we also find that models are very sensitive to subtle pixel noise. Now we're going to look at an analysis of video language models instead of video models. So here the main difference is we're taking in two modalities. We're taking in both language and video. And the reason this is important is because now we have 2 vectors of attack instead of 1. And these models are very important because they're often used to learn generalizable features that are used for a variety of real-world applications. Oftentimes that can be visual reasoning, text-to-video retrieval, and they can even be used for downstream tasks like action recognition from the previous work. So as mentioned before, most of the robustness studies are focused in images. So again, we want to provide more robustness benchmarks in videos. And we need a deeper analysis to understand what the strengths and weaknesses of these generalizable models are and what kind of areas of improvement are necessary. So our benchmark focuses on the latent space of these models. And so what that means is when we're going to focus on text to video retrieval. And so here's an example of that where we have our videos going through a visual encoder and our text going through a text encoder. And the video and the matching text should be very close in this latent space, more similar than the text from another video or another text. So this is ideally what we want our model to look like, because this means they're matching the correct text to the correct video. However, when we add perturbations, such as for the triangle, this is a spelling error, as an example here, we can see that now it's actually closer to the other video. And so it's causing some problems in the latent space that will result in incorrect text-to-video retrieval. So here's an overview of the models very quickly. So all of them use a dual stream approach where they have one encoder for vision and one encoder for text. Most of these approaches actually use a pre-extraction of visual features because they want to represent longer time segments. So they take a time segment of the video, get some features, and pass it to a transformer. One exception is this FIT model that takes in both raw video and text. And then Univeil and Coot both use a cross-attention mechanism after the dual stream encoders. And Coot is special because it also takes in pre-extracted text features. It's not fine-tuning their text encoder. So again, we're using the same video perturbations as the previous work, so I won't go through and detail those. However, we also have text perturbations this time with 3 high-level categories. The first is the natural category, which is to simulate real-world occurrences such as spelling errors, a changing of tense, and some gender bias, or some gender swaps. And then we also have a machine level category, and this is interested in generating not only more variety in our perturbations, but also because in the real world deployment, it is oftentimes that input to one model is the output of another, and that's becoming a more often occurrence. So it's important to include that as well. And then finally, we have our synthetic perturbations, which is just looking to probe the models for their behavior. Since all of these architectures utilize transformers, we focus on positional, such as shuffling order. And we also are just interested in seeing what they're attending to, so we drop a lot of information to see how the model reacts. So we use two data sets. The first is MSRVTT with some examples here, and these are very short 10-second clips. And then our second data set is UCOOP2, and here we have long cooking videos that are split up into shorter clips, so they represent longer complex activities. So now I'm going to go through some of the insights we found from this benchmark. The first is that models are much better at the shorter video clips rather than the longer. And we also find that the FIT model is actually significantly more robust and higher performing. So just to be clear, on the x-axis, we have our text-to-video retrieval at 5. That means the correct match was retrieved at 5 queries. And the relative robustness is on the y-axis, which is, again, the relative drop in performance from the clean score to the perturbed score. And so here we see FIT is both more robust and higher performing. And this model takes in raw video and raw text. However, when we evaluate it on the UCOOP2 data set, it's unable to perform. So while this is a great benefit to have this performance, it doesn't work very well with long approaches or long videos. So on the text side, we see that models are noticeably more robust than the vision side. However, we see the exception with COOP, which uses pre-extracted text features, and it's quite noticeable the difference there. And so this may indicate that pre-extracted features are just less robust overall because a lot of the vision models also use pre-extracted visual features. So this may be one of those indicators. So when we're perturbing both vision and text, we again see that models are better with these shorter, more distinguishable videos as compared to the longer, less distinguishable videos. So now we're going to look at some specific aspects. So oftentimes we have perturbations or real distribution shifts where we as humans can still recognize what's going on. So we can still see here what's going on. We can still read this sentence. However, when we test these models on them, they actually struggle quite a bit. So here we're showing the results for the models on the visual side of things when we're perturbing just by adding some pixel noise. On the x-axis, we have severity 0 to 5, where 0 is no corruption and 5 is our greatest corruption. And on the y-axis, we have our text-to-video retrieval at 5. And as you can see, as the severity increases, models drop their performance very significantly, with the exception of FIT that does quite well. But even so, it does drop at a certain point. When we're looking at text, when we're just changing one single character in one of the words, we can see here that from the clean score indicated by these horizontal lines and the perturbed score by the top of these bars, that there is a noticeable drop just from changing one character. So as you can see, models are struggling with these human perceivable corruptions. So we're also interested in seeing how models might learn some gender bias. So here we swap gender references either to all female, all male, to neutral. So neutral would be, for example, a little girl does gymnastics becomes a little child does gymnastics. And so one of the things that's interesting is on that neutral, we find that models on zero shot are actually performing very well. They don't see a difference because in reality, the caption still matches the video. However, when we fine tune or train from scratch, we do see there's some small drop in performance from that clean line to that bar. So this may indicate when we're fine tuning on these data sets, it's either learning some kind of biases or it's using, or in the same way, it's using it as a memorization or a hack. So as we mentioned, video time is very important. So we want to evaluate how these models perform on temporal corruptions. So here we're looking at jumble, which is just shuffling those frames. And again, we have the severity 0 to 5. And on the y-axis, we have the different data sets with text-to-video retrieval at 5. And as you can see, there's not a lot of change. The models stay quite consistent, indicating that frame order is not as relevant here. So now we're going to probe the behavior by dropping information. So here we're dropping either nouns or verbs, or just one random verb, one random noun. So what we find is models are surprisingly robust to just dropping information. We do see that they might be more sensitive to nouns versus verbs. So here we're comparing where we remove all verbs from the caption, and we're comparing it to where we remove just one random noun, just one. And as you can see, the models, when all the verbs are removed, are more relatively robust compared to when you just remove one noun. So this might indicate that they're attending more to those objects rather than those activities. So here's just another interesting observation. Here I am visualizing using a TSNE algorithm, the embedding space of the models, where the X's are our text embeddings, the captions, and the circles are our video. And I'm using arbitrarily the UCOOP2 recipes. This is just for visualization. They're not trained on the recipes. But what we see is that from left to right, the model performance increases. And what we also see is the gap between this embedding space gets larger. So this is an area of improvement where we should understand, is this the ideal scenario? Do we want this? Why is it performing better if there's a larger gap between them? And our metrics are based off of the similarity. So in summary, we find that models are typically more robust when text is perturbed. We also see models are more robust when they're pre-trained, even in some cases zero shot where they're not pre-trained on the target data set, they're fine-tuned on the target data set at all. It's not necessary that models are struggling with long videos, but it's more that they're less distinguishable because they're complex activities with sub-actions that might be very similar versus shorter videos that are very distinguishable between each other. And we do find some evidence that models might be attending more to scene and objects based off of their preference for nouns and their ability to handle any kind of shuffling versus motion and anything. So now we're going to talk about our conceptual robustness of visual language models. And so here we're looking at image language models. And the reason we need this evaluation is because we need to know more about the specific failures and why they might be failing on these benchmarks. And we also want to try and understand what these models are learning as conceptual consistencies under the hood and what hacking might be occurring for them to perform so well. And so image language models have lots of real world applications. On the right, I actually have an example of that where this is input into the built model. And we're asking it a question and it's going to produce an answer for us. So this is a real world application you might see of these models. So our benchmark is inspired by cognitive psychology. We want to probe these models in the same way a cognitive psychologist might probe a brain. We're going to use prompting as one of those methods where we create a text template and pass it to our model. So for example, a photo of an attribute and object would be the template here. And we propose 3 data sets to do this. The first is probe R, and we're looking at how models understand the objects' relationships to each other. The second is probe C, we're looking at how attribute and object relationships are. And probe B is finally looking at the object's relationship to its background, whether that's just the background or other objects in the scene. So here's an overview of our models. We have a bit more variety here. We have CLIP, which is a dual encoder, dual stream model with no cross attention. We have Flavo, which is similar to CLIP, but it has a cross attention transformer after. And then Bridge Tower is similar to Flavor, but it has these bridge layers, which add even further cross attention at the same time as their modality specific encoders. And then finally, we have VILTS, which is unique in that it's a single stream approach, which takes in both image and text into a transformer architecture. And so we're going to talk about the first data set, which is probe R, and it's built off of visual genome. And what we're doing here is we're taking a ground truth relationship, subject, predicate, and object, and we're swapping either the predicate or the subject. The predicate will be swapped with something that doesn't make sense to occur between the 2 objects, and the subject will be switched with something that's not present in the image. So we're going to make several comparisons here. The first is between the ground truth relation and the prompt where we switch the predicate with one that is not likely to occur. The next is between the ground truth and where we're switching the subject to something that's not present in the image. And finally, we're going to compare it also to a subject only, where we have a photo of in just the subject with no relation in secondary object. The metrics we use for this is the mean confidence of the ground truth prompt and the accuracy of selecting the ground truth prompt. So our next data set is looking at those attribute objects, and it's built from MS COCO. And the first one is where we're switching the compositions or the attributes to its antonym. So this should actually be quite easy for models because not only are they switching the attributes, they're also the opposite of the original attribute. The next is where we actually switch the object and keep the attribute the same. So for example, a photo of a wooden bed and a photo of a wooden bench. And the metrics here are a bit more complicated because we have 2 images and 2 prompts. The first is a text score where we have 1 image and 2 prompts. And the image score is where we have 2 images, 1 prompt. And the group score is whether both of those were correct. Finally, we have the probe B data set, which is looking at that background information. It's also built from MS COCO. And so the first variation of this is where we remove just the background and replace it with a different type of background and keep all objects present. Then the second variation is where we remove the background and all other objects to see how much those models are using other objects present in the image to help predict one object. And so when we're replacing these backgrounds, we're actually replacing them with a filler that's either a solid color, black or gray, random noise, or random scenery that doesn't contain objects that are present in the image. So also to measure the robustness and disentangle the relationship between the filler, we also have a variation where we add just a single patch of one of those fillers to see how the model responds as well. And so we'll have an original image, a patched image, and a modified image. So the metrics here, we're going to look at accuracy or mean average precision if there's multiple objects, and the mean change in confidence or the change in confidence. So now we'll go through some of the insights from these. So the first is looking at those object relations. We have some examples down here. So here's where Bridgetown Built was successful at selecting the correct caption. For example, a photo of a light on the wall versus a light constructed with wall. So this one's incorrect and this one is correct, and these two models got that correct. Now from the results, we actually see models are better when the object is swapped, but the attributes stay the same. So here's where the predicate is swapped, that's the accuracy, and this is where the object is swapped in the accuracy. And as you can see, the models perform quite better. However, one thing to notice is that single stream architecture, where both modalities go into one transformer, we see that the model's performance decreases quite significantly when it's just compared to the object only prompt. And so that might mean that it's getting very confused on which to pick when there's only one object and an object relationship in another object, meaning it might be hacking and trying to just focus on objects. Furthermore, we do see quite noticeably that the modality and cost attention simultaneously is actually really noticeably more performing than the other models. So just a little bit peeking into that black box of what's going on. Here we have that built model with a single stream, and here we have that no cost attention model clip. And as you can see, when we pass in a photo and several prompts, the attention is always going to stay the same because there's no cost attention. And you can see it's focusing on the man, so it's prioritizing that object, the man. And when you look at the text side as well, you can see that it's prioritizing the objects here. It's not very often looking at those predicates. And with the built model, you can actually see one of the benefits here. You can see the attention changes based off of the prompt that's being passed. For example, you have a photo of a man on a skateboard, but you see it's paying attention more to the skateboard than the man. And then when you see that the object that's no longer present, the object's not present, you can see that the attention varies a little bit. So you can see it actually struggling when the prompt's passed. Now we want to look at that probe C data set where it's attribute and objects. So here we have an example of what that looks like again. So this is when we're switching the composition, and when it has object, we're switching the object. And so as you can see, models are better at matching the image versus text. So we have two prompts and one image. So this may indicate these models are better at determining between text and visual features. We also see that the Flava model, which is the dual encoder with a cross attention, performs better in the reverse, where it has two images and one prompt. So there might be some architectural differences that favor the differentiation between text versus differentiation between vision. So we wanted to categorize these attributes to see which models are better at what types of attributes. And so we have our higher level categories here and our results over here, where the y-axis is those categories, or sorry, the x-axis is those categories, and the y-axis is that group score. And so what we see is that the cross-attention models were better with materials and color, while the modality-specific were competitive with pattern expression and shape. When looking at just the clip model, because there's a lot of variations of this clip model, and it's used very frequently in a lot of downstream approaches, we see when we have a transformer-based backbone, we set it up better with color, expression, and shape, while the CNN is better than texture, patterns, and materials. So we do see that different backbones are attending to different things. So now we want to look at the background and how models might be using the background to recognize objects in the scene. So here we're just removing the background and no other objects. So we're measuring the mean average precision of the objects being present, or the relative robustness from the score on the original image in either the patch image or the modified image. And so what we see here is that some models improve from the patch to all background being removed. So this is that single stream built model. And what this means is that when we're adding a patch, the model performance drops noticeably bad. So that means when we take out the patch and we actually replace it with a full filler, it's actually performing better than with just the patch. So this is showing quite a significant weakness in that single stream approach we've been talking about. When we're looking at mean average precision, we can see that models are very consistent in their performance, and it's quite high as well. And we can see this by that triangle shape. However, again, with that built, we can see when we're looking at the patched image, the performance drops quite noticeably. So again, we're seeing that just adding a single patch to the image makes the model performance drop. So now we're going to look at the same kind of information, but instead we're comparing when all the objects are present versus when only one object is present. And what we see is the performance between recognizing that single object doesn't change that much. I mean, just looking at the confidence, it's very small changes here on the y-axis, and then the x-axis, and the y-axis has our categories of objects. And as you can see, that change in confidence is very low. So this kind of indicates that the models aren't necessarily using the presence of other objects to recognize a single object. So we learned a lot about these models through this benchmark. So we want to explore how we might be able to improve the dual stream approaches, because one of the problems with that cross modality or the cross attention and modality specific simultaneously, it's very expensive and very difficult to work with. But the CLIP model, which is a dual stream encoder, it's very easy to extract those visual and text features and use for downstream text. So what we want to do is try and improve them by fine-tuning CLIP according to the things we're interested in, which is based off of those previous data sets. And so here's an example where we're using an image text matching loss, and we have our anchor image in a negative where we're doing the same kind of thing as probe R. We're using a predicate that doesn't make sense for the two objects, and then our positive ground truth statement. And we do the same from text to image as well. So we have our text with the correct statement, our negative in the image. And we do that again with attributes as well. And we make it more challenging as well because the negative has all of the attributes in the caption switch with an antonym. So the negative becomes quite obviously the negative, and the positive stays quite positive. And because we want to prevent this catastrophic forgetting of its original feature weights, we also employ something called patching, which is where we linearly interpolate the weights from the original model with our fine-tuned model to try and maintain some overlap there. And so what we do find is that performance drift is a weakness. We see that from our fine-tuned models that the performance on ImageNet, which is an image-based object recognition data set, drops quite noticeably. However, we do see that when training the text encoder only versus the visual encoder only, or both at the same time, we see that it shows the most improvement in comparison. In summary, we showed a lot of data sets and a lot of results, but for probe R, we find that they're really weak when the predicates swapped, even when they make no sense. We find that the cross-attention and modality-specific learning simultaneously has the biggest boost in performance and robustness. When we're looking at those attributes and object relationships, we find again that cross-attention is better with materials and color, and that the modality-specific is still competitive with pattern, expression, and shape. Finally, when we're looking at removing the background, we find that the transformer-based approach built was very weak when just adding one single patch, but better when we replace the whole background. We find that they're strong at object recognition, and they don't use other objects in the image to help. So this may mean that they're not using those background cues for object recognition. However, we do see even with those minor changes that some objects might use other objects, but still not enough to provide that evidence. And finally, with CLIP patched, we showed that even light fine-tuning of selective hard negatives might help improve these models. However, you really do need to attend to that catastrophic forgetting. So overall, this body of work, we've made several conclusions. The first are visual models are not robust to just a subtle addition of noise. We found that transformers are generally more robust. We have that visual language models have greater potential for interpretability. And finally, visual language models might learn consistent underlying concepts, and that we may be prioritizing object recognition instead of those relationships between those objects. So here's my body of work at ECF. And thank you. Do you guys have any questions?